Thank you for your kind introduction, and also thank you, audience, very much for joining our webinar about Aryne in synthesis in our Thieme journal. Let's say synthesis. So let me before starting, let me briefly explain our journal synthesis and how successful our special issue about Aryne is. Okay, can you see this these arrows? It's okay. So then synthesis is a well-established journal in a sense, more than 50 years old, and it has many reviews and also full papers in chemical synthesis. And currently editor-in-chief is Professor Mark Lawtens from Canada, and also the special editor for reviews and short reviews from Germany, Professor Martin Esterreich. And then Corina Schindler, Professor Corina Schindler is serving as an editor for special topics and issues. And also we have regional editors, including me, and we are handling your high-quality manuscript. Then not only Corina is an editor for special topics and issues, but not only Corina, but also all the editors can organize special issues or special topics. And this time I organized a special issue about Arynes in organic synthesis by inviting Professor Suguru Yoshida here as the guest editor and also as a co-chair of this webinar. So because Aryne is very, very important in organic synthesis, and the special issue was really, really successful. And it is now composed about 15 papers, and all of them are really, really of high quality. Okay. And here you can see some contributors, Professor Paul Knohel and Miyabe Hideto, Suguru Yoshida, Jiajin Tang, who is the one of the speakers in this webinar, and so on, Professor Yamaguchi, Shindo, Chris Jones. And then here you can see highlights. Professor Christopher Jones from the UK wrote a very comprehensive review about Aryne in reactions. That's a kind of landmark review that everyone have to check. And also the other nice review is from Professor Hideto Miyabe from Japan, and he wrote a regio-controlled reactions of 3 halo Arynes, as you can see here. And Professor Paul Knohel also wrote a nice paper about pyridine as a nice building block for pyridine-derived compounds. And also one more nice paper from Professor Takigawa from Kyoto University that deals with about the synthesis of highly complicated cyclic framework, starting from very simple starting material. So these are just only 4 examples, but the other papers are also of high quality. And please take a look at the special issue. That will be soon published in December, I hope. And so in addition to the special issue about Aryne in synthesis, but here you can see some other special issues. Maybe the most recent one can be Cristina Nevado's special topic about her award. And also this one is a deadline is November 30. The same deadline is November 30 here about the phosphorus redox chemistry. And here you can see more about the upcoming special issues. If you are interested in submitting these papers, please do so by using this manuscript central online submission system. And also, if you are interested in Thieme and also synthesis and other journals, please use this QR code to access Thieme journals. And also, if you like to stay in touch with us, Thieme Chemistry, you can follow Facebook, Twitter, LinkedIn, and also Weibo. Then you can use these SNS or social media to see what's going on in Thieme Chemistry. So this is that's it for the information about Thieme and the synthesis. And let me start my the scientific part of this webinar about Aryne in synthesis. So let me start introducing Professor Suguru Yoshida. Okay, Professor Suguru Yoshida graduated from the University of Tokyo, and then he moved to Kyoto University, and he received a PhD from Kyoto University in 2007, 8, 9. 9, okay.
9,
and then he was a postdoc in Kyushu University and also the University of Hawaii as a visiting scholar. And then he came back to Japan, and then he was an assistant and associate professor in the Tokyo Medical and Dental University.
Yes.
Okay.
Yes.
And then he moved to the Tokyo University of Science about 2 or 3 years ago as a principal investigator, and now he is pursuing his independent research about developing new methodologies in organic synthesis. He's really a leading and a young rising star in Aryne chemistry in organic synthesis. And today he will be talking about Aryne chemistry for the synthesis of diverse heterocyclic compounds. So Professor Suguru Yoshida, please.
Yep. Okay. Can you hear me?
Yes.
Okay. Okay. Thank you very much for kind introduction, Professor Yorimitsu. I'm Suguru Yoshida from Tokyo University of Science, where my lab studied last year. It is my great pleasure for me to talk about our recent synthetic Aryne chemistry on this WebCheminar today. Okay, I will start. Okay, first of all, as a guest editor with Professor Yorimitsu, I'd like to thank all contributors and editorial team members for publishing this special topic on Aryne chemistry in synthesis. I believe these nice papers will be attractive for broad readers and showing great potential of Aryne chemistry. Okay, today I will be talking about Aryne chemistry for construction of highly functionalized heteroaromatic compound. I'm studying on Aryne chemistry since this is a key intermediate for synthesizing complicated functional molecules from simple sturdy materials in short steps. This is because we can perform diverse Aryne reaction without reacting functional groups useful for further transformation, such as cross-coupling reaction. Sorry. So we have, in this decade, we have developed a number of transformations through Aryne intermediates. Indeed, we have developed new methods to generate Arynes, various transformations through new Aryne intermediate having functional groups, and new Aryne reaction. Today, firstly, I will show this topic on sequential Aryne generations through this Aryne intermediate having triplet group. After this topic, I will show new heteroaromatic type Aryne chemistry and new reaction using organosulfate will be shown. Okay, let's start. As you know, Aryne reacts with diverse molecules due to its strained triple bond. For example, Aryne easily reacts with diene 1,3 dipoles and electron-rich alkenes to afford these cycloadducts. And recently, a number of transformations involving insertion reactions of Aryne intermediates into sigma bond have been developed. So by these reactions, we can construct a wide variety of heterocycles through Aryne intermediates. In addition, we can perform regioselective reaction when using 3 substituted arynes. Let's say substituents, as shown here, at 3 positions facilitate regioselective addition and cycloaddition reactions. This is due to the strong inductive effect by electronegative atoms, as shown here. This selectivity can be predicted easily by DFT calculations of Aryne intermediates. So we can synthesize a wide range of aromatic compounds regioselectively by understanding this point. Due to good reactivities of this Aryne having triplet group, we can synthesize a wide variety of functionalized aromatic compounds from simple steric material, as shown here, and through this Aryne and this Aryne and this Aryne. At first, I will show the generation and transformation of this Aryne intermediate having triplet group. The triplet group is known as a good leaving group, so we can use this functionality in various transformations, such as cross-coupling reaction. And we are also interested in its strong electron withdrawing nature in Aryne reaction. The part I want to emphasize is the good accessibility of this iodo type Aryne precursor. This is synthesized from cheap resolution only by iodination and torfidation. We achieve this synthesis in 100 gram scale in one batch. This Aryne can be generated from this precursor by this method. We recently found that thymethylgrenal reagent activates this iodo type Aryne precursor to generate arynes. Magnesiation and following beta elimination of the triplet group leads to Aryne generation. Since this Grignard reagent show milder reactivity than conventional activators such as butyl lithium, we can generate a wide variety of functionalized Aryne intermediate without damaging these functionalities. So we can generate this Aryne by this method. Let's say, in the presence of this electron-rich alkene, treatment of this iodo-type Aryne precursor with silane-methyl-Grignard reagent in ether provided this cycloadduct in good yield regioselectively. So we can prepare a wide variety of aryl torreflate by this method, and we can use this functional group by palladium catalyzed cross-coupling reaction as shown here. During this study, Professors Akai and Ikawa also found this Aryne can be generated from this silicon-type precursor with fluoride ion. And in addition, Professor Yan Li reported this elegant reaction, domino Aryne reaction, through this Aryne intermediate. We also developed a variety of transformations through this Aryne intermediate bearing triplet group. I then explain sequential aryne generation through this aryne and this aryne. The amino acylation of this aryne intermediate having triphate group took place smoothly to afford this type of orthosylyl aryl triphate regioselectively. This is also an aryne precursor, so we can synthesize diverse alanine derivatives through this aryne and this aryne. The amino acylation of aryne intermediate was firstly reported by Professor Hiroto Yoshida at Hiroshima University. In his elegant work, he succeeded in this synthesis by using bulky silyl group due to the weak N-silicon bond with fluoride ion. In contrast, under our fluoride-free conditions, we succeeded in this synthesis in good yield without using bulky silyl group. And we can generate this type of 3 amino aryne from this type of precursors. For example, a regioselective addition and cycloaddition took place through this aryne intermediate due to the electronegative nitrogen. By coumarin synthesis reported in these papers, we achieved this synthesis, 5-aminocoumarin. It is not easy to synthesize by conventional method. This 5-coumarin shows nice fluorescent properties. Well-studied 7-aminocoumarin emits blue fluorescence. In contrast, 5-aminocoumarin shows orange fluorescence in which large stock shift was observed. This is a clear example that new reaction leads to new functional molecule like this. In the case of silyl sulfide with this aryne bearing triphate group, we can synthesize this type of sulfide type aryne precursor. For example, here we achieved this sulfide type aryne precursor using this silyl sulfide. And further transformation leads to this new organosulfur skeleton formation. Indeed, treatment of this aryne precursor with acid anhydride in the presence of this sulfur oxide provided this diaryl sulfide. In this reaction, CS bond formation like this and demethylation reported by Professor Yorimitsu. This reaction allowed us to prepare this diaryl sulfide having these functionalities for aryne generation. So then fluoride ion activates this silicon to generate here this aryne, and further transformation, further cyclization results in this organosulfur skeleton formation. So let's move to the next aryne generation through CC bond cleavage. This type of benzene-fused cyclobutanone derivatives can be prepared from this aryne precursor by 2+2 cycloaddition. We found these arynes can be generated through CC bond cleavage, as shown here. These reactions were found by Dr. Uchida. He was awarded a SynFact Poster Prize at International Conference on Heterocyclic Chemistry in Regensburg. The reaction he firstly found is shown here. Treatment of this ketone with phenylithium in the presence of furane provided this 3-component coupled product in high yield. This reaction was triggered by nucleophilic attack of carbanion to this carbonyl group, affording this alkoxide intermediate, and then kick back like this, and liberation of this triflate generates this aryne. This was trapped with furane. In this reaction, we can use alkyl and heteroaryl lithium, and we can construct these skeleton by this reaction. And this type of ketone is a useful intermediate for constructing organonitrogen skeleton like this. Furthermore, we found this aryne generation from silyl aster with fluoride ion. Fluoride ion activates this silicon, and then CC bond cleavage and B elimination of this triflate generates this aryne intermediate. This was trapped with this azide region selectively to afford this cycloadduct in good yield. We were excited by these tricky new reactions. But before this publication, Professor Yang Li reported this aryne generation from this silyl aster as shown here. This publication indicates a competitive situation on modern synthetic aryne chemistry. We then found the generation of this aryne having beta keto moiety. Mukayama-Aldo reaction of this ketone with this silyl aster, silyl ketone aster afforded this alcohol, and treatment of this alcohol with this potassium carbonate in this furane afforded this cycloadduct through alkoxide intermediate and this aryne intermediates. Through this type of aryne intermediates, we succeeded in the synthesis of this potent anti-cancer compound in this scheme. So we have developed various transformations through sequential aryne generations. This is a key intermediate. Then I will explain new heteroaromatic type aryne chemistry on the next single slide. To make a long story short, we found these heteroaromatic type aryne called as hetarynes. These were generated from these precursors having iode or silyl group, and we revealed that these new hetarynes were very useful for constructing highly functionalized aromatic compounds. Lastly, I will show new aryne reaction using organosulfates. Okay, due to the potential structural complexity of organosulfates, we can design a wide variety of aryne reactions using organosulfates. Firstly, I will show this benzothiophene synthesis directly from aryne intermediates with alkynyl sulfides. Fortunately, this reaction was highlighted in chemistry reviews as new path to benzothiophene. Since sulfides attack aryne intermediates reported in some papers, we imagine that this benzothiophene can be formed from aryne intermediate through CS bond formation and further cyclization. After screening of the reaction conditions, we succeeded in the efficient synthesis of this type of benzothiophene in good yield from this aryne precursor and alkynyl sulfide. In this reaction, CS bond and CC bond formations took place smoothly, and further protonation and deacylation here also proceeded. The scope of this reaction is wide, so we can prepare diverse functionalized benzothiophene by this reaction. A plausible reaction mechanism is shown here. Firstly, this aryne was generated and then sulfur attack to this aryne, and further cyclization provides this carbonyl intermediate. And then protonation like this and deethylation provide this phenolphthalein product. Since deprotonation at 2 positions with LDA as a base took place smoothly, we can prepare a wide variety of functionalized phenolphthalein by reactions with electrophiles. So we achieve this synthesis of pentacyclic compound from this aryne precursor and this alkynyl sulfide. This aryne reaction and further deprotonation iodination afforded this dihalide. And then we succeeded in the double anion arylation catalyzed by palladium using this aniline, affording this highly fused new compound. So we have developed this phenolphthalein synthesis directly from aryne intermediate. I will show next aryne reaction using this sulfoamines. We recently found sulfoamines react with aryne intermediate to afford this type of product by 2 CN bond and 1 CS bond formation with CS bond and SN double bond cleavages. At the beginning of this study, we at first attempted this addition reaction of sulfoamine with aryne intermediate. Since amines easily react with aryne intermediate to afford this type of adduct. So we attempted this reaction, but the desired adduct was not obtained. And we found this type of product was obtained. CN bond formed at meta and CS bond at also. And here, phenyl group was migrated from S to N. After optimization of the reaction conditions, we succeeded in the efficient synthesis of this type of diaryl sulfide under these conditions. In this reaction, we can use a wide variety of aryne precursors as shown here. In particular, when using 3 methoxy arynes here, CN bond formed at meta and CS bond at also. In contrast, here, when using 3 silyl arynes as intermediates, the selectivities were switched as shown here. CN bond formed at also, CS bond formed at meta. This is due to the electron donating silyl group. We can use various sulfoamine and here, chloro and bromo groups were tolerated. When using unsymmetric sulfoamines, here, more electron deficient allyl groups were selectively migrated from S to N, so we can synthesize these radioselectively. In addition, when we used here this sulfoamine having methyl and taryl group, here this primary amine was obtained in moderate yield through demethylation without migration of taryl or methyl group. In the case of using cyclic sulfoamine, we can synthesize this 8-membered ring product. We showed plausible reaction mechanisms. Firstly, generation of arynes and following nucleophilic attack of nitrogen to this aryne intermediates and further cyclization provides here this 4-membered ring intermediate. And then ring opening like this and SN aryl type migration of electron deficient aryl groups would provide this type of diaryl sulfide selectively. By this Aryne reaction, we can synthesize this type of complicated aromatic compound by assembling these simple stirring aromatic compounds. So in this new Aryne reaction, we can leave bromo group in products. So we can synthesize diverse phenothiazine by cyclization. For example, when using sulfamine having methyl group, we can synthesize this primary amine and then palladium catalyzed intramolecular coupling reaction. Here, we can prepare phenothiazines. Here is another synthetic route for N-aryl phenothiazine. Indeed, this Aryne reaction afforded this product, and then treatment of this product with this base afforded here this N-aryl phenothiazine through migration of this taryl group from S to N and further cyclization between this sulfur and this carbon. In this reaction, at first, here, proton grabs this proton, generates this nitrogen ion, and Smiles rearrangement and further cyclization provided this N-aryl phenothiazine. This reaction can be performed in one-pot manner, and due to the wide scope, we can synthesize a wide variety of N-aryl phenothiazines. This new Aryne reaction can be applied to related reaction using sulfoxyamines and sulfoxides. In particular, in the case of sulfoxide, CO bond formation and CS bond formation here with migration of this aryl group from S to O took place. In this reaction, bromo group was tolerated, so we can conduct palladium catalyzed cyclization to form different heteroaryls like this. When using cyclic sulfoxide, we can synthesize this type of 8-membered ring product by ring expansion from 5 to 8. And to our surprise, when using here this sulfoxide having orthofluorophenyl group, this migrated product was not obtained. Instead, here, direct cyclization here proceeded smoothly to afford this cyclic sulfonium salt. We are continuing to develop a new reaction using organosulfur compound with arynes. In summary, we have developed a number of transformations through Aryne intermediates for assembling simple sterling materials to provide a wide variety of highly functionalized aromatic compounds in short steps. This is the final slide. I'd like to thank all co-workers at TMDU and my laboratory. And financial supports and here this reagent supply very helpful for our studies. Thank you for kind attention and joining this seminar. Thank you very much. That's all.
So thank you very much, Professor Yoshida, for your great showing us a great chemistry about Aryne to synthesize highly complicated heteroatom containing molecules. It's quite powerful method. So for the audience, do you have any questions? Maybe if you have any questions, you can write in Q&A. Okay, and then so may I start asking question? So in your very last part of your talk, you showed us a very interesting ring expansion reaction of dibenzothiophene monoxide.
Yeah.
That's really powerful. So is this chemistry applicable to benzothiophene oxide or thiophene oxide? Thiophene oxide can be too reactive, maybe, but what about benzothiophene oxide?
We have probably that reaction can proceed, but we haven't tried yet. So probably we can.
Yeah, that's quite interesting.
Yeah, thank you.
Usually, you know, this is eight-membered ring, right?
Yes, 8. Yes.
The size. And then do you have it? And also, my next question can be so the carbon-carbon bond cleavage from the cyclobutanol.
Yes.
And then in that chemistry, probably the counter cation can be very important.
Yes, exactly.
So, do you have any comments on that? Lithium, maybe sodium, potassium, or some other counter cation?
Thank you. Yeah, it's very important. For example, here in this reaction, if phenyl magnesium bromide Grignard reagent was used here, we can prepare alcohol without CC bond cleavage in the reaction at low temperature. On the other hand, here this CC bond cleavage took place when using this phenyl lithium. So in this reaction, counter cation is very important. And in this case, probably fluoride ion activates this silicon. So in this case, we can use various fluoride ion source.
So this is not about the Aryne chemistry, but if in this case, if the OTF unit is missing,
yes,
if there is no OTF group, still ring opening proceed or not?
No.
Or no?
No.
OTF group is assisting ring opening.
Yes, exactly. OTF group is very electron withdrawing group. So this type of CC bond cleavage is facilitated by this group. Yes.
Okay. So I can see some questions from the audience. So congratulations for the brilliant presentation. And what is your opinion on the advances involving the preparation of functionalized Aryne precursors?
Yes, preparation. Yes, okay.
Functionalized Aryne precursors.
For example, here, okay. In the case of iode type Aryne precursor, prepare that good accessibility is a strong point. So it's easy to synthesize because iodination reaction is well studied rather than silylation. So we can synthesize diverse, highly functionalized aryl, also iodotriphylate having functional groups. So we have achieved this study, this generation method.
I see. So in that sense, you use the trimethylcellulose methyl linear reagent.
Yes, yes.
So this is really a key reagent for your generation of arynes.
Yes, exactly.
Good.
Sorry. Here. Yeah, this Grignard reagent had low nucleophilicity and low basicity. And this can activate this iodo group due to the here facilitation by triphylate group. This magnesiation facilitated by this group, so we can use this mild silyl methyl Grignard reagent to generate aryne intermediates.
So
this is very useful. Yeah.
So this allows us to use functionalized aryne precursors. That's great.
Yes, exactly.
One more question from the audience is that how about the reaction of N-aryl or N-alkyl sulfilamine with aryne instead of N-sulfilamine?
Okay. Here. Sorry. Okay. We have tried these two examples in the thioamination of aryne intermediates. Here, in the case of methyl group, here this methyl group was missing in the product. Here, the demethylative reaction took place. In this reaction, here, migration of this aryl group or methyl group did not proceed, as shown here.
So sorry, maybe I asked you a bit in a way, but his or her question is that what about N-alkyl?
I see. N-aryl. Okay, N-alkyl or N-aryl. Oh, thank you. Yeah. Now we're studying on that type of reaction, and it's succeeded. Yeah, we can. N-alkyl and N-aryl we can use.
So you can install one more substituent on the nitrogen atom.
Yes, exactly. Yes.
Great chemistry. So any other questions from the audience?
So Professor, you should have a small questions. First of all, very nice talk for your chemistry. So I noticed that for both your first part of your third part, you use a lot of 3 substituted iron precursor. I'm just curious about the reduced selectivities. So I understand that there is a mode proposed by Gog and Hoek on the effect of the 3 substitution. Because our group also tried to use some of the 3 substitute ones, but we didn't get sometimes we didn't get very good reduced selectivities. I'm just curious, do you think in addition to this effect, do you think the temperature or the nature of the nucleophiles will affect this reduced selectivity control?
Yes, the electronegative atoms, this is very, very important. For example, alkoxide or amino group works in this aryne reaction as electron withdrawing group due to the inductive effect. So in our case, almost perfect radial selectivity was observed in the addition reaction, and this type of cycle addition reaction when using 3-amino or 3-alkoxy or 3-halogen substituted arynes.
Oh, okay. Thanks.